and the positive point that are sort of holding up the line. Okay? They may be, in this case, they're almost touching it, but generally they're going to hold up, and the line you're looking for is the line where the two support vectors for that line are farthest from that line in a perpendicular distance sense. Do you understand what I'm saying? So the reason you said this is the best is because this is the support vector here, this is the support vector here, and this distance are farthest. In fact, actually what you'll wind up doing is you sort of think of a convex hull. You sort of make an imaginary smooth hull. And then you're talking about the closest points between these two that are holding up that line. Those are called the support vectors. So from the point of view of finding this line, support vector, the perceptron was just finding any line that minimizes the error. The error is 0, it's good. So that finds what's called the feasible set. Anything in the feasible set was good enough. But now you're going from feasible set to optimal line. So if any of you know anything about linear programming, for example, there would be linear programming constraints and there is an objective function. If you just give the constraints, that will be like a higher dimensional polytope. Any point in that polytope is a feasible solution. And you're looking for that point in that polytope where this linear objective has the highest value. And if you remember how you did it in your grade school, you would see that a linear objective is like a line, and you are trying to push this line up this polytope, and the last point of its touch to the polytope would be one of the corners, because it's a polytope. And so you just search for the corner that makes that line, that particular linear objective, the highest value. Right? So this is basically like going from feasible to optimization. In linear programming, you are looking at an optimization which is a linear objective. It's a line. Unfortunately, here what you're doing is, this is the picture, right? This is a convex hull, this is a convex hull, this is C and D. Those are the closest points. And you want the line such that the distance between C and D is the maximum. And you want the line that bisects that line. Perpendicularly bisects that line. That's what you're looking for. So, I am minimizing this objective subject to a bunch of linear constraints. The linear constraints basically say that C and D are in the convex hull of the respective points. And talking about convex hull of a point essentially is convex combination of a set of points will be in the convex hull. Now what is a convex combination? If I give you x1, y1, x2, y2, let's say these 2 points, then alpha 1 times x1, y1 plus alpha 2 times x2, y2 will be called a convex combination as long as alpha 1 plus alpha 2 equal to 1. And alphas are positive. I'm sorry, they don't actually have to be positive. So alpha 1 times the point 1 plus alpha 2 times the point 2. So that means you're actually doing arithmetic multiplication. Notice, for example, this is very close to, if alpha 1 and alpha 2 is 1 by 2 and 1 by 2, what do you get? You get the centroid of these 2 points. That was in the convex combination. But so are many other points around it. So this is how you compute convex hulls. Okay? So you set up basically an optimization problem where the linear constraints are about convexity in terms of the points in the positive training points and the negative training points. And the optimization function is this quadratic function. Everything was good up until the quadratic part. Linear programming won't work with the quadratic functions. Except it turns out, if you study it a little bit more, because many of you probably don't even know linear programming because CS normally doesn't push it. But if you are in OR, you may have heard of linear programming. but even they may not have heard about quadratic programming. But suddenly, this idea requires you to understand quadratic programming. Turns out there actually are pretty efficient techniques for quadratic programming. And so you apply the techniques for solving this quadratic program, and you will find the optimal line. Okay? And if you are interested in the perceptron code that the project had, they had perceptron and they had this other idea called Mira. It's not support vector machine, but neither is it just find any line. It is finding a line that is sort of greedily optimal. Not the most optimal, but sort of better than the worst. And they kind of, if you play with the Mira, then you can see why, and it turns out that that actually is easy enough to implement without understanding quadratic programming. So they threw that in. Okay? But when people talk about support vector machines, they're talking about actually solving this particular quadratic programming function problem. Okay, so the pieces that you want to remember, of course, is max margin. The line should be farthest from the closest points on the two hulls. Support vectors, the two closest points are holding up the line. Those are the support vectors. And optimization is quadratic because the line has to be essentially bisecting the two closest points in the convex hull. Now you don't know what the points are because those points are in the convex hull. Okay? That is essentially, and then it turns out that, I don't want to go into this, but the whole point of, if you get a chance, take courses in linear programming. They have this whole idea of duality. The idea of duality is, in one, basically in any linear program, you have objective and constraints. In the dual, constraints become variables. So they basically reformulate the problem. I can't go into the actual technical details, but typical people basically understand this whole idea of duality of a program, and sometimes you do the primal salvage solution for a while, dual solution for a while, then primal, then dual. And this is sort of like the bidirectional search, going from forward direction for a while, backward direction for a while. It's a bad analogy, but something to keep in mind. Now, it turns out that when you take this quadratic function and find its dual, it turns out that dual, what's called the Lagrangian dual, essentially winds up being in terms of these dot products. Just remember this point, because it will be useful in the next two slides. You're not yet going to get the break. The other two slides, and then you get the break. Because then I don't want you to tell me that somehow you hear about some random idea called support vector machines. And the next one is kernel machines. Everything is done today, before the break. And you might die because of the thirst. But anyway, won't have any thirst for the knowledge after that. So you have support vector machines, right? And you have perceptrons. They're both solving the same problem. One seems to be solving it slightly better because it's finding the best line, not just any line. Now, but both of them are essentially solving problems where the decision surface is a linear surface. They're both looking for lines. They're not looking, one is not looking for curves, the other looking for lines. They're both looking for lines. Now, we did talk about the fact, so for example, could we have solved, maybe I should ask you this, but think about this, could I have solved the XR problem with the support vector machine? How many of you really understand why it is no? Okay, if you understand, because it's a line, XR, if you remember the reason you could not solve XR, because if I can go back further and further and further, there was no line that you could draw. Yeah, these are the positives, these are the negatives. There's no line that separates all the positives from all the negatives. It's not the question of how nice the line is, whether it is solid or dotted. There was no line. So, if I'm looking for a particular kind of person, right, if none of you have that property, finding the best of you still doesn't get me anything. Like for example, I'm looking for the best basketball player. If none of you actually know what basketball is, then finding the best of you still would be as good as finding anybody. Okay? So support vector machines still don't solve XR, and they don't solve any problems which require nonlinear decision surfaces. Perceptrons could be extended to multi-layer neural networks which do solve that problem. Right? So the question is, can you extend support vector machines, which seem to be this competing? It's like the Pepsi for the support vector machines. I mean, support vector machines are the Pepsi for the perceptrons Coke. And Coke is now coming up with whatever it's Mountain Dew or what, I don't know who makes what. But it's coming up with a multi-layer network. Now, the support vector side has to come up with something to compete. What do? It turns out that's where these kernel machines come. So the kernel machines trick is the following. So basically, this was nonlinear surfaces directly using multi-layer neural networks. If you want to learn nonlinear surfaces, one idea is learn them using multi-layer neural networks. This part you already know. The other idea is take the data, transform it into a higher dimensional space. I'll explain to you in a minute what that means. Now, if you transform any data into higher dimensional space, there is always a dimension where the data is linearly separable. And it's a tricky point to understand, but here is a way of thinking about it. If the data has 10 million points, which are all of 100 dimensions, I can tell you this much. If you go into 10 million dimensional space, where each dimension is just the point itself. If the point is there, then you will get 1 in that dimension. If the point is not there, you will get. So the first point will have 1 in that dimension and 0 everywhere else. The second point will have 1 in the second dimension, 0 everywhere else. If you do that, then you go and randomly put pluses and minuses, you can see that you will be able to shatter any plus and minus. There's this idea of shattering. If I give you some number of points and you get to put pluses and minuses on them, then can I shatter it by drawing a line such that one is separate from the other? When I expand the dimensionality, you will always be able to shatter it. Now it turns out that nobody talks about expanding the dimensions of the data. Everybody talks about reducing the dimensions. If any of you have heard anything about data mining and data anything, it's always dimensionality reduction, not dimensionality expansion. Because any random guy can expand the dimensions. But now we want to do that. Why? Because if you expand the dimensions, you do it right. You may not have to go all the way to 10 million dimensions, and you may still be able to separate the points with a line. So, a highly telling point is this example. This is also in the textbook. Okay? So, here are my negatives, here are my positives. Clearly, the circle is separating the negatives from the positives. Circle is not a line. That much we know. Right? And so, this is x dimension, this is x1 dimension, this is x2 dimension, and these are the points in this space. Now, suppose I take this x1, x2 point, and for every x1, x2 point, I blow it up, I make it bigger in terms of x1 square, x2 square, root 2 x1, x2. Those are the dimensions. You can compute these numbers, right? So you had 2-dimensional data, you now got 3-dimensional data. Now each point, you know which point became which 3-dimensional point. So you knew whether it is positive or negative. So this is the 3-dimensional surface. It turns out that beyond this I can't draw pictures for you. Okay, that's why I took this. So in this 3-dimensional surface, if I did this, notice what happened. All the negatives came here, all the positives came here. Can you see a nice plate sitting in the middle, separating those two? That shows you that in this case at least, blowing it up to higher dimensions separated the positives from the negatives. What I'm saying to you is there's a large amount of theory about Hilbert spaces and stuff, which basically says that you can always separate positives from negatives if you blow it up sufficiently high. In fact, Hilbert spaces are infinite dimensional. Somebody woke up. Okay? Hilbert spaces are infinite dimensional. So you take x1, x2 and make it into an infinite dimensional point, which will be a vector in infinite dimensional space. And then I'll have a nice plane in between. Hilbert is happy. Hilbert is the guy with the infinite dimensional hotel room, right? So he's happy. Now, the way, basically, if I could do this, now if I find the equation of this plane in these new coordinates, I can always invert it back to this. Voila, I got. I basically did line separation here, and I came back here, it became a curve. Looks good. Nice trick. The only thing, of course, is all you have to do is consider all possible ways of blowing up the points, check if they are separable, and when they are actually separating them, you could have done perceptron here. But somehow Pepsi guys came up with this, so it is connected to support vector machines more. Okay? So the support vector machines, basically, they will try to find the plane that is maximally far from the two regions. And then you will get it back, it will be a nice little curve. Now, as I said this, it's a great metaphor as to how the thing works. What you don't know is how to actually pick the right way to do this. And furthermore, if the two steps are really required, which is one step is blowing up, and the other step is getting back, it seems like a pretty darn hard thing. So there comes this huge idea, and it's totally a mathematical idea called kernel trick. And since math would not give you anything useful, you just take what math gives and say it is useful. Understand this is actually very true. Okay, you take what math gives and find uses for it. Okay, so it turns out that, remember, I said in the support vector machines, right, you had the dual form of the support vector machines corresponded to an optimization which involved dot products between the points. You can think of dot products between the points as a kind of a similarity metric. And the people who are particularly wildly, nodding their heads are the ones who know something about information retrieval, where, for example, they take the dot product between two vectors and say that's similarity. Dot product is close to dot product is a sort of a distance. Distance is connected to similarity. Small distance, high similarity. Now, one interesting thing that you can show, that has been shown, is if you take the dot product that was there between x1 and x2, and you replace this is almost like this old Folgers commercials where we went and replaced the coffee they were drinking with this alcohol and asked them how are they feeling. So you replace the dot product with any arbitrary similarity function. It's no longer dot product, it's just an arbitrary similarity function. It might say x1 minus x2 whole square plus y1 minus y2 whole square, the whole thing square root. That will be Euclidean. Or, basically you can do any polynomials, you can do sine waves, you can do logarithms, etc. Any nonlinear similarity metric, if you do this. When you do this and solve the support vector machine, basically this is the optimization that you are doing for the support vector, right? If you just change the normal dot product with this arbitrary nonlinear similarity metric, anything which you feel like, which makes sense in the domain, then it would correspond to, in theory, going to some high dimensional space, finding a line that's like the best in that high dimensional space, and coming back. I wanted to do this before the break so that it will come with really turning heads. Okay, so this is the kernel trick. You don't know which space it took you to. You see what I'm saying? Given any arbitrary similarity metric, it takes you to some space. So now, of course, the question is no longer which dimensionality should I take it to, but to make my kernel machine work, what similarity metric should I use? I have 5 different similarity metrics. Let me use all of them and see which one fits the data best. That's what kernel machines people do. Instead of deciding how many dimensions do I need to throw the data into, which is an infinitely large choice, here you say, for my domain, so for example, let's say for a set of text vectors, dot product is a good idea. So is something like LSI dot product. So is something like, some weighted product. So is something like some squared Euclidean norm. And I basically use my domain understanding to come up with the similarity metric and throw that in and see if it improves performance. If it improves, then the kernel must have been good. That's kernel trick. Okay? And when you do this, in a sense, so these are the different kinds of kernels people can use. They can use polynomial kernels, which are like, the P norms. They can use basis function kernels, where you take the 2 vectors, take the norm, square it, and take the exponent of it, minus of that. You can take a neural network itself can be taken as a kernel function, and you see what I'm saying? So it's just any similarity. And what is interesting is that if you were actually, instead of doing dot product, if you just use an arbitrary similarity and use perceptrons, you would have gotten some line. You would have thought it looks like, you would have gotten some answer. Right? But this one, what it's saying is, because of the kernel, when you come back, what you will get would not at all look like, it can actually work in cases where you have situations like this. This is a completely piecewise separated region. And for the right kernel, like this is what's called a polynomial kernel. For the right kernel, you will find, you'll be able to actually fit to this data quite well. So the deepest explanation I can give you is you just changed one, I don't know how to do this choice, into another, I don't know how to do this choice. Okay? One was infinitely large, the other also is infinitely large, but you only know 4 of them. Do you understand what I'm saying? We just happen to know only 4 or 5 similarity metrics, so I'm happy enough. I tried all 4 of them, I'm stuck. Whereas if you know that's an infinitely large set of dimensions and you have to pick each of them, then you'll say, I really didn't get done yet. Okay? That's the deepest explanation I can give you in terms of why kernel machines actually seem to work without really having to go through. Yeah. Now, people aren't talking as much about kernel machines most recently because this stuff isn't working well enough. But it works much better than simple support vector machines and simple perceptrons. Take 10 minutes break and we'll come back and check.